Hi everyone, welcome back. And while you're here, I remind you of doing one of the two things or both. One, hit the subscribe button if you haven't already done so. And two, just hit the thanks button if you feel extra generous. In this video, I'm going to talk about how you can perform instance segmentation, the quotations around instance, because we're not doing a true instance segmentation like you would do with mask or CNN or some other approaches, but we are trying to achieve an object segmentation result by performing a semantic segmentation. And how are we going to do that? A couple of weeks, in fact, more than a couple of weeks ago, I did a video on the topic of converting your masks, binary masks, into by adding borders, actually, not converting your masks, but adding borders to your objects in your binary masks. And why? My explanation was so you can actually use these borders as another class as part of your semantics. So we are going to perform multi-class semantic segmentation and use the border class to identify or to detect the boundaries between objects so we can separate them and in a way kind of simulate our instance segmentation. This is far easier than doing all the mask RCNN and all that. Of course, mask RCNN would be good, and I encourage you to learn about it, and one day when I have time I'll record some videos on the topic, but this is a method that I follow and it works great. So I plan on telling you this, and this is a change in the gear from our last videos where I talked about how you can deploy your model, all that, but I'm going back to my roots in terms of image segmentation. And in the next couple of videos also, I'll show you a couple of cool libraries that help us in performing amazing segmentation. But let's jump into this topic now. Now that you know exactly what the plan is, let us look at the code. And one quick note before jumping into the code, I plan on using the segmentation models library instead of using my own custom multi-class unit segmentation, because with this I can actually load pre-trained weights that these guys are making available as part of the different frameworks that they have. I did many videos using these segmentation models, so I'm not going to talk a lot about this. So I'll leave this reference as part of the description and also as part of the code that I'm going to share with you over GitHub. But the plan is for us to use unit, as that's my favorite network. And one of these I will use ResNet backbone with pre-trained weights. It makes our segmentation a bit faster, yeah, our training a bit faster. Okay, now let me truly jump into the code. There you go. There are 3 steps here. First thing, I'll quickly talk about generating this border in case you haven't watched my previous video that I believe was please look at my channel under tips and tricks 31 and look for generating border video if you haven't watched it before. But I will go through the code in a very quick way. That's step 1 is to generate borders to our data set. So where is our data set? This is our data, and this is my image that we are going to use as part of our training. The UNet network, and then these are the masks that I would have normally used, but I'm going to take these masks and generate borders around them. In fact, I have already done that, and here are the borders around these objects, but I'm going to walk you through that process. Once the borders are generated, the next step is training. How do we do the training? Like I mentioned, I'm going to use the segmentation models library. Here is the link. I'll share that with you. And let's train the multi-class unit network. And then I'm going to show you how to now take that prediction. You can how to take the segmentation, of this multi-class and then apply Watershed segmentation to segment your images into a instance segmentation or individual objects. And why not finish off by adding some measurements, like to measure what's the roundedness and various parameters that we can extract out of this. So that's the plan, and I hope this will not take too long because the code is already there. So step number 1, generating the border. How do we do that? We are going to do that in a very simple way. We will take our mask. For example, let's look at a mask that has a couple of objects close by. We'll take a mask And for each of these objects, we are going to erode by a pixel or a couple of pixels, erode these objects. And then from that point on, dilate it by 6 or 7 pixels. Why? When you take this dilated image and subtract the eroded image, you get the border. That's it. So we are defining a border like 1 pixel into the objects and 5 or 6 pixels outside the object. That's pretty much it, as simple as that. So that's exactly what this code does. First, I define a erosion kernel of 3 by 3 all ones, and I use that kernel to erode using OpenCV into my image right there. And you can define number of iterations, like how many iterations you would like to do. I usually do one on images like these. If you have extremely large objects and you want to define a thicker border with 2 pixels, 3 pixels into your objects, go ahead and do that. And that's the erosion step. And now we need to go dilate from the eroded image. And for that, I'm defining a kernel size of whatever the border size that you're interested in, like maybe 5, which means my kernel size is 11 by 11 of all ones. And I'm going to use that to dilate my image, my objects right there. And then I am going to take the dilated images, so the dilated objects, and subtract the eroded object. And whatever the border is remaining, I'm going to assign a pixel value of 127 to that. So at the end of this, I will end up with images like these, where I have my background with a pixel value of 0, my objects with a pixel value of 255, and the border with a pixel value of 127. That's it. Now, if you work with images where your objects have a pixel value of 1, of course, go ahead and change the code to customize it for your specific case. I mean, in my case, it's 255, so that's it. So this is the essence of this generate border Python file. And of course, that's the function that I defined up there. And down here, I'm going through each file in the directory to apply the generate border method and saving the images. That's it. Not much to discuss here, as basic as it gets. Now let's step to the next step, how to train a multi-class semantic segmentation. Probably the reason why you're watching this video anyway. So for that, let's go ahead and import some of the libraries here. So I am going to import TensorFlow, and I'll print out the version. So I oftentimes forget to do this, include this. I'll make it a habit to include that as part of my code, so you know exactly which version it actually worked on, in case you're watching it sometime later on. Okay, so this is the TensorFlow, and I am also going to import my segmentation models, which is the library that I just showed you earlier, and everything else should be pretty much straightforward. Glob to walk through the files, and OpenCV, OS, NumPy, and matplotlib for plotting, and of course from Keras, I'm going to import normalize and mean IOU to report any metrics right there. So let us, I don't know why I'm importing TensorFlow twice. Sometimes I tend to do that. And let me import Keras so I can print out the Keras version. So let's run these lines. Okay, so that's done, and I'm using TensorFlow 2.4.4 and Keras 2.4.0 in case you wonder. Okay, so now we have to do two things, right? Once import all my images in the images directory, and corresponding masks that are in masks with border directory right here. So these are the two things we need to import and capture as NumPy arrays. So how do we do that? It's pretty straightforward. So from this directory, from the images directory, I'm using glob.glob. Now you get the files, and I'm just adding a counter right there. And for each image that ends with .tiff, because this is the directory path, right? For each image that ends with tiff, as long as the count is less than total images to load, go ahead and why am I doing this? Let me go down to show you. Backbone, where is it? Sorry about this. Mask reshaped and convert directory path. I went through this. So first I'm loading the images, and next I'm actually loading all the masks exactly the same way. No point in explaining the masks part, but anyway, I'm reading these images, individual images, using OpenCV, and I'm reading them as RGB, even though I have a grayscale image. because the model that I'm going to import expects an RGB image. So instead of changing the model and all that stuff, I'm like, okay, I may as well read my images as RGB. Why read them as gray? So that's exactly the justification for right there. I am not resizing my images as I'm reading because I already cropped them into the size that's required, which is 256 by 256. If your images are of different size, obviously take care of that right here. And I'm appending my images to the empty list I created there. And of course, at the end of it, I will convert my, my list into a NumPy array. I do exactly the same with my masks. So let us go ahead and run all of these. By the way, I'm reading, I made this a little complicated than it needs to be because I have 1600 images and I don't want to train all 1600 images. I want to load only 500 images for now. That's why if count is less than, otherwise all of this count part is useless. I was wondering why I did that. Anyway, to make sure that the training happens in a decent time while I'm recording this video. So let us run the lines we already discussed about until this point. So at this point now, it should show up with 500 images, each 256 by 256 by 3 for images. And for masks, it should be 256 by 256. That's it. So right there. So you see our images, 500, 256, 256, 3. I have 500 corresponding masks, each 256 by 256. So far, so good. Okay. Now let us go down. Let me create some space here. Okay, let's go down and look at the next part. This is a multi-class classification, so I need to encode them into one hot encoding, for example, into categorical. So let's go ahead and get started by the process. So first of all, I'm using scikit-learn's label encoder to convert them into to encode the labels, and I'm encoding those labels down here. As you can see, we have done this many times in the past, so I'm not sure at what point it gets too basic, but let's go ahead and encode these. And it's doing its job. And now let's see what are the unique values in our encoded data set. So the unique values are 0, 1, and 2. 0 for the background, 1 is for the border pixels, and 2 is for inside. I mean, you can print out and see which one is what, but 0, 1, and 2 corresponds to the 3 classes that we have in our masks. That is it. And by the way, I haven't done one hot encoding. I lied right there. I'm going to do that later on right here. You could have done it right there, but I'm going to do it later on. First, I have to convert my 0, 127, and 255. I converted that into 0, 1, and 2, and then I'll do this in the next step. It's completely up to you how you would like to do it. Okay, so now that we have our masks encoded, from all we did with this step is go from 0, 127, 255 to 0, 1, and 2. Now that we have that, let's go ahead and expand the dimensions of our masks input, because right now our mask input, train masks encoded original shape. If you look at that original shape, our input is right now 500 by 256 by 256. You know that to go into a neural network, we need extra dimension added to this one. So that's exactly what I'm doing right there. To my axis 3, add, expand the dimensions. So now if you go back, it's 500, 256, 256, 1. Okay, so far so good. Now that we have our training and masks, training images and training masks, let's go ahead and use our train test split to split them into training and test, or training and validation data sets. And I am splitting them 80% test size, 80% test size. That's probably because I want this to be done pretty fast. That means my test size, let's just go ahead and change this to 50% test size for now. Or in fact 20% test size. I just want to show you how the process looks like, but I have already trained it, so I'm not going to waste your time. Okay, so my test size is 20%. So what is my total data set? 500. Of those, 20% are for testing, remaining 80% are for training. That's it. Okay, so that part is done, and now let's go ahead and print class values in the data set. Or it's again another sanity check. I just add as many print statements as I can. So class values in the data set are 0, 1, and 2. Good. Now we need to convert that into categorical. So that's exactly what I'm doing right there. Convert to categorical using the keras.utilities categorical. And of course, number of classes equals to how many? right? How many ever that we defined right here. So let us go ahead and do that. And now my white rain categorical, let's go ahead and do the masks and all of these. And now let's go ahead and look at my categorical shape. It should be 256, 256, 3, because you have 0, 1, and 2 that we have encoded right here. The background, the border, and the object itself. That's why you have 3 channels right there. Now the data set is all ready for multi-class segmentation. So that is the next part of the code right here. And I should remove this. I mean, these are the parameters. I was testing with multiple models, so I just put some reusable parameters up here and then different models, but let's just look at some of the parameters. Number of classes, how many do we have? 3 classes here, 0, 1, and 2. And what activation do we want to use? Of course, this is multi-class, so softmax. And the learning rate, I'm going to fix it to 0.301, which is a good starting point anyway. And the optimizer I'm going to use is Adam Optimizer. The reason why I'm putting all of those here is I was experimenting with different settings. This is how you should normally do. Okay, and in addition to that, I am defining the loss functions. I'm defining a combined loss of dice and focal losses. And I am adding more weight. In fact, in this example, I'm adding equal weight to dice loss and focal loss. You can add an additional multiplication factor to focal loss if you want to add importance to focal loss. And in this example, maybe I should do 2 or 3 times focal loss, but that's okay. I have already trained it, so no point in changing right now. Let us go ahead and, of course, what metrics do you want to track while you're training your model? I'm tracking the intersection over union score, and I'm also tracking the F score. For both, I'm setting the threshold to 0.5. If you don't know what I'm talking about, you haven't watched my previous videos, and if I keep talking about every little thing in every one of my videos, it is going to be, they're all going to be extremely long videos, so I hope you can go back and watch my other videos on the unit topic. Okay, so we did run all of these. Of course, nothing going on there, just assignment of variables, no computation. Now comes the unit part. I am going to use ResNet34 backbone, meaning the encoder is going to be ResNet34, and my decoder of the unit is going to be mimicked based on what we get from ResNet, from the encoder. So let's define my backbone as ResNet. There you go. And now let's pre-process our data. So far, we haven't pre-processed our data at all. That's because I want to pre-process my images. When I say pre-process, that means normalizing your data or whatever you do to your input images. I want to pre-process them exactly the way they got pre-processed using when they trained ResNet34. That's why from segmentation models, I'm going to get pre-processing with for ResNet34. So that's exactly what that step does, imports the pre-processing. And now I need to apply that pre-processing to my training data, to my input, right? Both training and testing. So let's go ahead and do that. This is my images, by the way. Obviously not the masks. You're not pre-processing the masks because our masks are all categorically, we converted them to categorical format, but now we are dealing with our 8-bit 0 to 255 input values. That's exactly what we are pre-processing here. Now let's define the model. What type of model do we want to define? Let's define from segmentation models. Let's define unit with a backbone of ResNet34. And for ResNet34, go ahead and download the ImageNet weights. And we have 3 classes. And we are using activation function of whatever activation I defined up here. Yeah, softmax. That's what this model is going to be. And let us do that. And there you go. My model is defined. And let us compile the model. I'm going to use the Adam Optimizer I already talked about, the total loss, which is the combination of focal and the dice loss right there, and the metrics that we want to keep track of. So with these, go ahead and compile the model. And let's print out the summary of the model so you can see what it looks like. Yeah, again, you can go ahead and study this on your own. Let us fit it. Let's just do 5 epochs for now so you can see how things look like on the screen. All I'm doing is model.fit method. Everything else makes sense. There you go. And I did this, of course, as you can see, for 100 epochs. And let us go ahead and import that in the next step to see how the segmentation looks like. So again, this is a multi-class unit segmentation where we defined one of the classes as the border. That's the only difference. So there you go. It's training. It's not that bad. I mean, it's pretty fast actually. It's just 20 seconds per epoch. So I could have actually done all 50 right now, but or all 100, but I've already done that to save your time and my time. So let us go down and load that 100 epochs and see how results will look like. So there you go. I am going to load the model. Of course, you know how to do that. Keras.models. I am going to load the model right there. And if you are loading it, do not forget to add compile equals to false, or add information about your loss functions and other details like metrics. Otherwise, it doesn't know what total loss means. So you have to tell the system that you are, if you want it to compile, that these are the loss functions that you have used. I've done this again many times in the past, so I'm not going to explain how to do that, but I'm going to mention that you should be doing that. Okay, so from our test images, let's go ahead and import some random images and plot the result. That's it. Let's see how good the result looks like. Let's go to plot right there. So there you go. So this is your test image. That's my test image right there. And there is the testing label. This is the ground truth mask. And this is the prediction on my test mask. My prediction is doing an amazing job right there already. Okay, so let's take this prediction. And I mean, it's working fine. And now let's go ahead and use this model to predict. So at this point, of course, what you need to be doing is loading all your test images, or whatever images you would like to segment. Add those, segment them, and dump them into your local drive. Or as soon as they get segmented, go ahead and apply the watershed method that I'm going to show you right now. So to demonstrate that process, let me kill everything here. We don't need any of these variables, so you know exactly how things should behave when you start from scratch. And we got nothing, so let us import these libraries again. All I'm importing is the segmentation models and my load model from tensorflow.keras. That's it. Okay, now let's define our model exactly the way we just did. It's going to use ResNet34, pre-process the input. Of course, you have to pre-process your input exactly the way you pre-processed your training data. And let's go ahead and load the model that we just saved. Okay, and let us test it on some random images. So there is a test image. So let's go ahead and open a test image. And what do we do with the test image? We expand the dimensions, right? For the test image, because otherwise the dimensions are 256 by 256 by 3. We need to expand the dimension to make it ready for prediction, and we need to pre-process that. Same steps that we followed earlier, so nothing to explain there. And now we are predicting. Model.predict. There you go. And now once you predict it, then what you get, the output is a 3-channel output. Obviously, we converted that to categorical, right? I mean, the output is going to be in this categorical format. So we have to look at that axis and take the argmax of that, whichever wins along that channel. So that's the class that we are assigning. That's exactly what we are doing right there. And now let's go ahead and plot it one more time. This is nothing but what we have done a few seconds ago, but now I loaded a different image that looks a bit challenging. You see these two are right next to each other. With regular semantic segmentation, that would be one big blob. So I have one mitochondria right there, one right here, one down at the bottom, and then it thinks that there are a few pixels here. You can actually clear that out when you do your object sizing, like, okay, what is the area, what is the size of these objects, and you can say, okay, ignore anything that's smaller than like 50 pixels or something. We can take care of those in a minute. This is where, okay, so now we have decent segmentation. How can we use these borders to separate these two? This is a classic watershed segmentation. If you know watershed, then you know exactly what I'm going to do, which is from scikit image, I'm going to import these. So for watershed, you have to, the process is, you have to tell what the sure background is, meaning I'm confident that this black area is background. That is your sure background. you have to tell what the shear foreground is. I'm confident that these white pixels maybe erode a little bit into it and say that I'm confident that these are actually my mitochondria. What I'm unsure about is this area where I have this gray region. So that's the gray area where we need to get some clarity. So that is the unsure area. This is exactly what we need to define. That's what I'm trying to do here. My shear background is wherever the value, pixel value in my prediction image equals to 0. That is my shear background. So let's define that and let's look at the image. So this is my shear background. So all the pixels in bright is my shear background. All the pixels in black is not shear background. Okay. Now let's go ahead and print the unique values of the shear background because it is going to be 0 and 1. 0 is wherever I have no objects. 1 is wherever I have background. Keep that in mind. Now let's define the shear foreground. If you go back to this image, what is the shear foreground? This area where we have mitochondria is, I'm sure, that is mitochondria, which means wherever my pixel values are equal to 2 in that specific image, that is my shear foreground. Okay, let's define that and let's go ahead and plot it. There you go. So this is your shear background. That is your shear foreground. Don't confuse this with, oh yeah, that's already segmented. No, we have the border defined right there with a couple of pixels into the object and a few pixels outside. So we need to assign the border pixel to either background or to the object. That is our next step. But this is our area where we are 100% sure, or well, whatever the percentage is, that we are definitely sure that this is my mitochondria. And I am going to change the shear background. In this image, the background equals to 0 pixel value. Whenever you do this, whenever you do this type of operation, shear background equals to test prediction 1 equals to 0, this is going to return a Boolean array as output. 0 for false, 1 for true. That's exactly why your image right here, the background is with a value of 1. In this image, the mitochondria is a value of 1. That doesn't make sense. We need to change the pixel value of mitochondria to something else so we know that it's not the background. That's exactly what I'm doing down here. Yeah. So if you look at the unique value of shear foreground, it's going to be 0 and 1. So let's change all the 1s to 2s. So basically I'm replacing, if I run this one more time, you should see that my unique values are now 0 and 2. I just replaced my pixel values of 1 to 2 right there, so I can distinguish this from my background. That's it. Okay, now comes the unknown region. My unknown region is in my prediction. The pixel values of 1 is my unknown region. That's where this is, which is the border pixels, by the way. You can see that right here. This is the unknown region. These are the border pixels. And the entire exercise is about taking the border pixels as the unknown region and growing it into the objects so we can find the border between these two objects. That's pretty much it. That's what Watershed is. Okay, so now how do we do that? Again, I did a video on Watershed segmentation a long time ago. Go ahead and check that out. It follows exactly the same process, or go ahead and read all the text here. So I am using connected components right there on my shear foreground. So it gives me the markers. So let's go ahead and do that, and you'll understand what I mean by markers in a minute when I plot it. So there you go. So it took my segmented image with shear foreground and converted that into this marked image showing these are the markers. So this is where the regions are going to grow using this watershed. And we are going to stop when they actually touch these two in a minute. So again, I explained the reason why to this markers, I'm adding a value of 10. I explained that right there. So if you look at the markers right here, it's an ND array, and if you go, 0 and 1 right there. But the reason I'm adding 10 is we already have 1 assigned to the background. So let's not confuse between all of these. So let's just add 10 to it. You can add 20, 30, it's up to you. I'm just adding 10 right there. So again, now mark the region of the unknown with 0. So let's go ahead and do that, and let's show the image so it makes sense to you. So all I did was, you have your background with a pixel value of 1. Eventually, I'm doing all this to get my unknown region to have a value of 0, pixel value of 0. And you know the inside regions, we have a pixel value of 2. Let me repeat that. Step number 1, when we did our background, when we did our sure background, it assigned a pixel value of 1 to the background. We did nothing to it. We kept it. And then when we did sure foreground, it gave a pixel value of 1 to the foreground right there. We said, no, that's not acceptable. Let's go ahead and convert those into a pixel value of 2. So this got converted into a pixel value of 2. Okay. And finally, when we did the markers, when we did these markers, here in the markers, we are changing the unknown values to a value equals to 1. To a value equals to 0. That's why these are all 0 right there. Okay. This is how it needs to be to work with OpenCV Watershed. That's why I'm trying to do that. Now that the markers are all there, we just need to use our Watershed on our test image using the markers we just defined. So there you go. And the Watershed will be done. And now let's look at these markers, and there you go. So this is how it found the boundaries between these objects, and you're all set. Now let us go ahead and convert that into a labeled image. So into an RGB image. So I'm converting that into RGB right there. So it makes it colorful when I show the image on the screen. And we converted the label to RGB. There you go. That's your input image, and that's the segmented image. Input right there, and individual objects. And there's a little object right there. If you want, you can clean that up, which I'll show that in a second, but I hope this process makes sense to you. And as part of your scikit image measure, there is region properties and region properties table, which directly gives you the table. That's what I like to use. And markers. And if you want to report intensity parameters as part of your properties, then you need to supply your input image. So within these objects, it looks at mean intensity or whatever parameters you're interested in. So these are the properties I chose to report. So let's go ahead and run it, and let's capture that as part of pandas data frame right there. And in the pandas data frame, I'm saying if the equivalent diameter is not greater than 20 or less than 100, ignore those objects. That's how I take care of these little objects. So go ahead and do that, and then print out the table. Finally, there you go. And this is, and in fact, you can open the data frame right there, and this is your label number 11, 12, 13, 14, 13, and 15. 14 got removed because we removed it. And by the way, why did the label start at 11? Because we added 10 up here, as you can see, to the markers. So the labels 11, 12, 13, and 15, 14 is removed. And these are all the parameters. There you go. This is an entire project for you, right? I mean, you're taking an image and corresponding masks, and you're doing some sort of an instance segmentation. I said some sort because this is not true, but nothing wrong with this. It is giving the result that you want. If your goal is to measure the diameters and all kinds of morphological parameters for this specific image. I hope you guys liked this video, and in the next couple of videos, I'm gonna really talk about very nice libraries for instance segmentation, and or these type of segmentation powered by deep learning, obviously. And we are not going to do a lot of coding, but then we're going to benefit from someone else's coding already, which means we're going to import those libraries. So please stay tuned to this channel and subscribe. Thank you guys.